Okay, this is okay. But these are the boundary conditions which we choose. Okay, that before that C1 is a parameter, but we introduce another parameter C2. And we solve the equation of motion for fixed C1, C2 to get mu as an eigenvalue. Then we calculate the density using the solution. And then this C2 just corresponds to the value number density. And then this C1 is a parameter, another parameter which parameterizes the percentage of the chiral invariant mass of the nucleus. Then this is a result for the analysis of the chiral condensate sigma. Okay, defined by this. And this shows that in the vertical axis shows the density. Sorry, horizontal axis shows the density. Vertical axis shows the value of this chiral condensate normalized by the vacuum value. In that at vacuum, this it should be 1. Then when we increase the number density, or we go to the higher density region, the chiral condensate decreases. Means that this implies that the partial chiral symmetry restoration occurs. Okay, then these three curves or three lines correspond to the different value of C1. And this blue line should correspond to C1 equals 0.3. This black line corresponds to 0.1, and this red line corresponds to 0. Then this means that the more rapidly decrease for smaller C1 means that if the chiral broken mass, you have more percentage of the chiral broken mass, means that the chiral condensate decrease more rapidly. Or I should say that when the chiral invariant mass is, percentage of the chiral invariant mass is large, like this, chiral condensate decreases slowly. That is our result, and it sounds reasonable. And this is our result for the equation of state. Here, but again, the horizontal axis shows the density, vertical axis shows the chemical potential normalized by the value mass. And chemical potential starts from 1 at 0 density. Then chemical potential actually increases with increasing density more rapidly for larger C1. C1 is gone. Then this red line shows it corresponds to C1 equals 0, and this black line corresponds to C1 equals 0.1, and this blue line corresponds to C1 equals 0.3. Then this means that if you have more chiral invariant mass, that this new chemical potential increases more rapidly. But this is actually problematic because I wanted to reproduce the nature by including the scalar method. You know that if you know the nuclear matter, that the nuclear matter can exist because omega repulsion and the scalar attractive force mediated by the sigma or scalar method balance very, very subtle balance occurs. Because attractive, usually, that the nuclear theory says that omega repulsion is of order of 100 MeV, gives a potential. If you convert it into the potential, that omega repulsion causes 100 MeV repulsion. And the sigma attraction is order of 100 attractive force. Then after the subtraction, you have to get about 10 MeV attractive force, right? You know that the nuclear matter is made by the attractive force between the nucleon, two nucleons in the nuclear matter is of order of 10 MeV. This is you can see in the text. It implies that you must have some kind of attractive force. Means that the chemical potential should should become minimum at normal nuclear matter density. This 1 implies that the density is normal nuclear matter density. Then it should increase. Otherwise, we cannot exist. You know, this should decrease and increase. Okay, this is the reason why we exist here. You know, in this universe. Okay? But this model doesn't reproduce such nature. Then somehow, this means that the effective scalar attraction is not enough in this model. Anyway, still this in the holographic model, it is very difficult to reproduce our nuclear matter, okay, that our body. Then this is one reason is we don't have enough scalar attraction yet. Okay, this is almost same for any model. But anyway, this indicates that we need more attractive force. Anyway, okay. Although this doesn't reproduce the nature yet, but it is interesting to study the density dependence of the effective nuclear mass. If we define the effective nuclear mass by using the so-called mean field model for making a nuclear matter. Okay, here that in the nuclear model, something is straight. This is 1981. Okay. Anyway, this is more than 30 years ago that one nuclear guy analyzed the nuclear matter using a kind of sigma omega model, and this is the formula. And using this formula, okay, we can calculate the value of, we can extract this effective nuclear mass. Here that omega NN coupling, we can calculate this because we have omega meson included and the nuclear exists. The omega meson mass can be calculated from the product model, and this rho is the density of the which is input. And the Kf is calculated from rho and this way. Then we can calculate this and start. Then effective, actually, this is our result. Effective nuclear mass decreases with density. It is about 70% at normal nuclear matter density. And it decreases rapidly for smaller Shibata. That means that when the chiral broken mass, or mass originated from chiral symmetry breaking, is percentage of the mass of the chiral symmetry breaking is larger than decreasing more rapidly. Of course, it's natural, because chiral invariant mass will be not changed by this effect so much. Okay, then let me give us some summary of this chapter. We proposed the hologram mean field theory to study variable many system in the hologram QCD model. We obtained the equation state which determines the chemical potential for given variable number. That is, in a HR variable model, the chemical potential increases monotonically with density, which seems a reflection of the repulsion. But in the HR Sakai Sigmoid model, scalar method doesn't exist. We have only omega method. Then we have only repulsive force. Then the chemical potential should increase. This is consistent. But in the HIY model, the chemical potential also increase. And maybe we don't have enough scalar attraction yet. This model. I'm going to give us some discussion. Okay? Although I did not say explicitly, there exists an action vector meson condensation in our approach at this moment. Okay? When the solution of the mean field is substituted, this current does not vanish. Okay? Then, but non-vanishing this current implies that this mean field for this action vector meson exists. This implies that there is an action vector meson condensation, and which implies a breakdown of the space rotational symmetry. Then we have neglected this in the analysis of HI model in section of not 5.3, but 6.3. Inclusion of such effect may change the conclusion. But this is still this means that this mean field is still problematic, but we are trying to resolve this at this moment. But I would appreciate if you can find any solution for this problem. Okay, this is the end of chapter 6, and actually this is the end of my lecture. Okay, if you have some questions, I will answer.
Questions?
I wonder, okay, as far as I understand, the holographic acoustic is based on the correspondence between the gauge theory and the gravity. Here, you want to discuss the nuclear major, and then the nuclear forces come from the exchange of pions. This is not a gauge theory. So, how did you have the holographic model here?
Oh, okay, pion exists. Then, but the pion is iso triplet pion, right? The pion attraction gives a tensor, so-called, not a singlet, not a iso-singlet force. And the most important one is the iso-singlet force potential of the iso-singlet part to make a nuclear matter. And then you need the sigma meson and omega meson. Sometimes people say that the two pion exchange generate a sigma meson, and which causes attractive force. But pion is included here. But at this moment, I don't know how to include the two pion effect. Usually people replace two pion effect with sigma meson. Then you can reproduce the nuclear.
And I want to ask you, you showed us the dictionary at the
Yeah.
beginning of your talk.
Yeah.
Okay, now what's the field on the, for example, UV, and what's the effective field on the IR?
Oh.
When we discuss the nuclear major.
Yes, that's a good point. That's a good point. That as far as I know, that there is no definite way at this moment to nuclear matter. Then we are proposing this way. This is one way, but still, our proposal includes some problem. And yeah, no, it's very difficult to reproduce nuclear matter using a model at this moment. The one reason is that in the Hollow QCD is constructed in the large energy limit. In the large energy limit, baryon mass is infinite, right? Then the baryon interaction is in the sense that 1 over L is suppressed by 1 over C. Some interactions are suppressed by 1 over C. Then it is very difficult to include such effect, but nuclear matter is made by such very subtle effect.
Other questions?
Just a question. In your first part, you have a fermion and a gauge field.
Yes.
Yeah, can you just use a scalar and a charge scalar and a gauge field to do the same analysis?
First part means this.
I'm trying to. What's the crucible part to introduce a fermion? In the first part, it's just a fermion and a gauge field.
Yeah. This Sakai model, HRY model.
Yeah.
Yeah, this one.
Oh no, the previous. Yeah, okay, this one. You use a Dirac spinner.
Yeah, this is top-down model, and I cannot introduce the scalar field freely, but there is some proposal to include the scalar method into this model. Okay.
No, I mean use a scalar, replace a spin, a charge scalar to be spin the spin.
Oh, I see.
To do the same analysis.
Yeah.
If you get a similar result, then I would wonder why Sperron number is totally unrelated, maybe something like that. Is it possible to use a Dirac field?
I see. That's a good question. Actually, that this is almost if you use the scalar field, it's same at this moment. Then that might cause a problem. Then there is a analysis done by some people of this kind of analysis, where that instead of psi, instead of fermion, that the boson comes included. That is applied to the condensed matter physics. Can be applied because if you replace this psi with boson, okay, that might be applied to the condensed matter physics.
Further questions? Students? Well, if not, we should thank Professor Harada for this beautiful series of lectures.